Okay, so this will be the exam review for Energy Auditing Fundamentals. It is a 5-part exam. The first one would be a utility bill analysis. We're looking at heating degree days and a regression. Part 2, we're going to do some EMO math, energy management opportunities. Part 3 will be financial analysis. We're going to do that in red screen. And then we'll do kind of a practical piece, auditor knowledge, thermal image camera and blower door, and finally a HOT 2000 analysis. Getting right into the prorating of utility bills. So that's the process to equate utility bills to a monthly basis. Sometimes there can be more than one bill per month. If one bill covers more than one month, this can be tricky and can skew the numbers, and especially if that bill covers the summer months. So ideally this is for electrical. Also oil can be tricky because you can get where they only fill up half the tank or they fill up all the tanks. So it kind of depends on what the oil is. So electricity is much easier to work with. This is a sample of prorating. So here we have September. We got an invoice in September of 1,000 kilowatt hours on that 20th of September. On the 5th of October, we got an invoice of 600 kilowatt hours. 28th, numbers are there. Okay, the first thing we're going to do is determine how many days between those invoices. Like, for example, there is 30 days, I believe, in September and 5 days in October. So it'd be about 15 days for this bill. And, you know, this one's a bit easier. 28 minus 5 would be 23 days. And then you divide that by the kilowatt hours for that invoice, and that will give you the kilowatt hours per day. We did this in Excel, but this is just the theory of it, and you're more than welcome in the exam time to use Excel to do those, crunch those numbers for you. So just to show you the next step, so we really can't get anything off that 20 September because we don't know when the previous invoice was. But this one here, so we have 5 October minus 20 September is that 15 days. So the average kilowatt is the 600 kilowatts divided by 15 days. We get 40 kilowatt hours per day. And we repeat that for each of those invoices. The next step now would be to figure out for October, let's say, how much energy we used in October. So we see that there's 5 days here. There would be 23 days at this one, and then another 3 days from this invoice. So we take that from the previous one. We had 40 kilowatt hours per day here for those first 5 days. So we get the first part is 5 days times 40 kilowatt hours. The second invoice, which was the 1,050, well, we know we use all of those in the month of October. I did the math here, but realistically we can just take that number. The last piece, the 3 days worked out at 54.2 kilowatt hours per day. So we just add that in. So again, 3 days times the 54.2 is this number. We add all those three numbers up and we get a total of 1,412.6 kilowatt hours. Okay, so now we're going to look and say, well, why are we prorating the bills? Okay, we're prorating the bills so that we can do an analysis on those utility bills, and we can compare prorated bills versus a couple of things. We can compare against a product produced. We audited a master packaging this year. That would be a classic example, or some kind of widget or something. Weather is kind of the default. We can, especially here in Canada, where we're doing heating. If we're trying to break out oil in terms of hot water versus heating, degree days is always good. Occupancy, we could do school as well, so prorated bills versus occupancy of how much the school is used. And what are the benefits of analyzing these utility bills? Well, it's an initial correlation between energy consumption and plant operations. We can set savings targets, we can flag down issues, we can put estimates to energy management opportunities, and finally some benchmarking. So what I've done here is I've really tried to simplify this regression just so that everything can be as clear as possible. Okay, so I'm going to move over. What we're going to end up doing is, maybe we'll do it here, is we're going to plot things on here. And the bottom part is going to be our cooling degree days. So I'll go ahead and insert a text box here, and we'll call this the CDD. And then I'm going to put a text box in, oops, wrong one, text box here for KWH. And that looks a little weird, so I'll just fix it up here a little bit. Okay, so we have kilowatt hours on our y-axis and cooling degree days on our x-axis. And maybe I'll go ahead and label these, insert text. So this would be, I've strategically made this graph so that it works with these numbers. So my cooling degree days is going to go as high as 600. I have 1, 2, 3, 4, 5, 6 lines. So 100, and I'm just going to copy and paste this now and go copy, paste. And I'm going to bring it all the way over here and say this is 600. You know, normally we'd be doing this in Excel, but I'm just, again, I'm kind of simplifying it just so that hopefully the theory is clear. And on the y-axis, our highest number is 800, and I've got 1, 2, 3, 4. So I'm going to go in 200 increments on this one. 200. And that will be the first line. And I'm going to copy and paste that and bump that up to the top here at 800. Okay, so then I got to look at my, I've given you 4 months. In reality, we would want to do at least a year, if not 2 years. And I'm going to show you next year what that looks like. But so now I'm going to go ahead and plot those. So January would be, I'm going to go ahead and use this here, doohickey. And so January is 500, so it's 2, 4, 5, so right in the middle here, and 300, which would be right here. So there's January. I'm still on here. So my next one I'm going to plot is March. So I'm looking at 600 kilowatt hours, so that's this line here, and 400 cooling degree days, which would be this line here. So I'm right here in this little circle, and it's not doing what I want. There we go. And the next one would be May. So May again, 700 kilowatt hours and 500 cooling degree days, right in the middle here. And the last one being the 800 kilowatt hours and the 600 cooling degree days. Okay, my next thing I'm going to do is insert a line, and I'm going to go all the way. I wish I had a ruler here, but I'm going to basically draw this line down through here, and I'm kind of looking at that and saying I need to be in this corner here, and in the middle, and in the corner. Okay, and that there is my regression, and I've got 2 things that I'm going to interpolate off of this graph. The most important one here is this base load. So maybe I'll put a text box here. Back to the cursor and text box. So right here we see the base load. Not sure why that went like that. Text box. So right again, base load here. So 200 kilowatt hours per month of the base load. So that there would be, I put Bahama Electrical Appliances and Space Cooling. So that the base load equates to the electrical appliance in the facility. So 200 kilowatt hours used per month for all the electrical stuff. And turn this back on, and I get my graph back. So that, again, see where it intersects the y-axis at 0 cooling degree days, 200 kilowatt hours per month. So if I'd said, what is the base load for the year? It would be 200 kilowatt hours per month times 12 months, or 2,400 kilowatt hours per year. My next thing to do is to figure out the slope of the curve, which really is would be much easier in Excel, but we can certainly do it here. So the question is, what is the slope of the curve? So if I went over 100 cooling degree days, I go up 100 kilowatt hours, and you can kind of see that here. Or if I went, you could see 200 cooling degree days, which is here, I go up 200 kilowatt hours. So my slope is a perfect slope here, but my slope would be equal to, sorry to ink off, slope equals rise over run, and in this case we had equal to, and they're the same, 1 divided by 1 or equals 1. So if I had said how much, if there was 10 cooling degree days on a certain day, how many kilowatt hours would it take? It would be equal to 10 kilowatt hours. This is probably a more realistic of what you can expect in industry, and this actually is from the Georgetown campus, their oil regression. And so on the left is oil in liters, on the bottom is the heating degree days. And what we get here is Y equals mx plus b. So B is that baseline, which we talked about here, the base load 200 kilowatt hours per month, and we see that here. And in this case, it's 765 liters, or almost 766. The rise over the run is equal to 14.8, 14.8, and we see that here. So if we had a run of 100, we've got a significant amount of oil, or 100 times 14.8, which would be, we move the decimal spot 2 spots, we have 1,488 liters plus the base load of 765, and you can see interpolated up here, it's just over 2,000, which is really what we can expect for 1488 plus 765, about 2,200, and we can see that on the curve. The R-squared value is how accurate the linear regression is, and as these dots move closer to the line, we're going to have a more accurate regression, and our R-squared value will be closer to 1. I do not expect you to do that for the midterm. What I do expect is something like this, to be able to plot this, to tell me the slope, and then to interpolate off of it, to tell me what the base load is. If I gave you a month with X heating degree days, or a day with how many heating degree days or cooling degree days, to tell me how much energy that would take. And here it is. So what is the monthly base load? We had said 200 kilowatt hours per month. What is the annual base load? So 200 times 12 for 2,400. And if a month contains 750 cooling degree days, how much energy would it take? And this is a better way to look at it, but in our case, it's 750, because our rise over run is 1-to-1 ratio. And that will conclude the first part, the utility bill analysis. I understand there are probably a few questions on this.